Alrighty. Uh, what is up? Today we're going to be learning Haskell for the greater good. Uh, hold on. Alright. Learning Haskell for the greater good. We're going to read it online for free. What happened to the CSS? What? Who's screwing up my CSS? Oh. Well, no matter because I believe I have the Haskell book downloaded. Alrighty. Very strange though that this doesn't really want to work. Hmm. Client, what even is that? Oh, okay. So I'm gonna have to HTTP this. No. There we go. All good. Okay. A scale time. Purely functional programming. I've already read most of this, so just to recap, purely functional programming language, notoriously. In imperative languages, you can change things. So you said 8 to 5, and then you said it's something else. All right. In purely functional programming, so you don't tell the computer what to do, you tell it what stuff is. You tell it that the factorial is product of all the numbers from 1 to the number, list, sum of a list, etc. You express that in the form of functions. You can't set a variable something and then set it to something else later. If you say that a is 5, you can't say that it's something else later because you just said it was 5. All right. So if you call a function twice with the same parameters, it's generally guaranteed to return the same result. That's called referential transparency. Not only does it allow the compiler to reason, but it allows it to completely deduce that a function is correct and then build more complex functions by gluing simple ones together. It's lazy, so it won't execute functions until it's forced to show you results. All good. That way, when you want something from a lazy language, you can just take some initial data, efficiently transform it, and mend it so it resembles what you need at the end. Statically typed, very glad to hear it. elegant and concise. Really smart guys with PhDs. We'll be using GHC, the most widely used Haskell compiler. Compiler, but it also has an interactive mode which allows you to interact with scripts. All good. Alright, so let's do this. Bang. Bash shell. Do you want to add it to bash RC? Yeah, sure. Do you want to install the language? Yes, I want to install language server. Better integration of the stack. Yeah, I guess, sure, why not? Okay. That'll take a minute. In the meantime, you do L and then the name of the file. And then you can play with them. And if you change the script, just run it again or do R. Okay, I see. I'm ready. And we're waiting for it to do its thing. Okay, so let's start out with simple arithmetic. All right. All right, so I see you can't add a string to a number. It's about what you'd expect. Okay. So, like Rust, integers aren't necessarily typed until you use them with something that is. Alright, so foreign function successor. Uh, okay. Okay. Alright, looks good. But not mistaken, you can also do this. But this will not work. Okay, all good. Calling a function with several parameters is also simple. The functions min and max take two things that can be put in an order. Min returns the one that's smaller, max returns the one that's bigger. But that doesn't exist. There's this though. Okay. Right, I see. So this would be 100. And this would be what we expect. Okay, so all good. Oops. All right, so let's now make a file. Let's go to okay, I guess I already have something here then. All right, all good. Let's make a function that takes two numbers, multiplies each of them by 2, adds them together. Great. I see what it's doing there. We could also define it as x plus y, x plus y plus y. That is true enough. Testing it out is predictable. As expected, you can call your own functions from other functions that you made. I see, recursion. Well, this is actually not recursion, my bad. Okay, so this seems pretty nice. So you could even just do a double, which takes a float, and a float returns a float. And it says, okay, so double A and B means to, no, just to double A. So this only takes one parameter, actually. When you double A, you are adding A and A. Easy. So then I can do double 5. Nice, very, very nice and straight to the point so far. Now let's do if statements. Okay, double small number. I see. If, then, else. Nice, short, sweet, straight to the point. So, okay, well, what am I thinking? I guess, like, there's not really much else I can do, but double small number. If it's greater than 100, x, otherwise, x times 2. So, like, we could do this. Make abs takes a, no, I'm just gonna do as. Absolute of a and of a. If a less than 0, then negative a else a. Cool. So now, yeah, okay, don't run Haskell this. THCI L first. Absolute of negative 421. Okay, that doesn't work. Ambiguous occurrence. I'll call it abs too. Okay. There we go. It's a very basic absolute value function. Yeah, it's a statement, not an expression. I mean, it's an expression, not a statement, my bad. You can do this and you can add 1. Note the tick at the function name. You can put a tick at the end and you use a strict version of a function or a slightly modified version of a function or variable. Because it's a very... Conan O'Brien. Okay. Functions can't begin with uppercase letters. Alright. Function doesn't take any parameters. When a function doesn't take parameters, we usually say it's a definition. That's pretty nice. This idea that every constant is just a function, but it'll always return the same thing, which is why it's a constant. So, pretty neat. An intro to lists now. Okay, I see. So we use let to define a name in GHCI. So let a equals 4, a equals 1, and then a is now 1. So let lost numbers equal 1, 2, 3, 4, 45, 5. And then when I print that, oh good. And if I'm not mistaken, that's what's really going on. It's showing, which is the toString kind of. But anyway, I digress. So then, let's go back to lists. You can add to list with ++. The concatenation operator. Seen this before? I can even add it to itself. And let me make a function then. Double list of a equals a plus a. What does this say? List of anything into a list of anything. And I guess you call these functions x and y, so don't take a, I guess. But if I do this now, does lost number still exist? No, okay, let nums equals 1, 2, 5, 4, 2, and then double list nums, and there you have it. Very nice. Now, one interesting idea then is to have it repeat it a certain number of times. Now, I know I'm sure there are very good ways to do this in the language, but repeat list you know what, I'll read this section first, then I'll try and jump into that. So just to first write what it will take a list of some a and turn it into, it'll take a list of some a and then an integer. And it will return a list of some a, which is a repeated that many times. Oops. So lists are linked lists. I see. Right, so that means putting something at the start of a linked list is very good. syntactic sugar for 1 colon 2 colon 3 colon thing. That's very nice. That's very nice. These are all different things. Well, yeah, of course they are. If we want to get an element out of a list by index, use bang bang. Zero, 1, 2, 3, 4. So there's 0 next. Yep. You'll get an error, so be careful. Let me get, what happens when I divide by 0? Okay, so there are exceptions in this language. It's not what you need. I mean, like, at some times you will just need exceptions to exist. Because you can't divide, you can't treat every division operation as if it could fail. The lists can be a different length, but they can't be of different types. That's what I'd expect. Lists can be compared if the stuff they contain can be compared. Yep, this is standard. What else can you do with lists? Right. So, first thing, tail. Okay, so this is like rest, not really tail, but the rest of the numbers. You take the last, this must be linear time, however. Right? So it will read through everything and then it will take the last one in it. Okay, I don't know if I like that, but sure enough. Yeah. Head, tail, in it, last. Ooh, okay, I see. Hmm. So the fact that it throws an exception for that is not something I really love. The way Rust handles it maybe is nicer with it being optional, but I guess even then, let's grade things up. Alright, this is stupid. Why is it called null? It should be called empty. Obviously this is not true, but this is. Oops, this is. Reverse is a list. Alright. Take, okay, nice. Take 2 from nums. Yep, this is pretty standard. Drop or skip, but yeah. Drop 2. So this will give me everything except the first 2. You have maximum. I don't like the I don't know if I like the fact that it's spelled out as a compared to this, but takes the product, returns their sum. Oops, takes a list, returns their sum. Takes a list, returns their product. Takes a thing and a list of things and tells us if that thing is an element of the list. It's usually called as an infix function because it's easier to read that way. So if I do 8 element nums, I should get false. But if I do, say, 2 element nums, I should get true. Texas ranges. What if we want a list of all numbers between 1 and 20? Sure, we could just type them all out, but that's obviously not a solution for gentlemen who demand excellent. We'll use ranges. All good. 1 through 20. Very nice. If I do this, it'll take a sec, but point is, it should finish that eventually. Alright, well, we'll get back to that. You can do it with characters. This is not brilliant. I would much prefer if you could just, like, since it's lazy anyway, why not just make a function that skips every two of them? Hmm. Not to use them unless changes. That's fair enough. That is fair enough. Don't think it's ever really necessary. Alright, so this is still going. Right. Okay. You can also use ranges to make infinite lists by just not specifying an upper limit. Alright, great. Sure, you could do 13, 26 to 24 times 13. I see. But you could instead do 13, 26, etc. Take 24 of them. Right. Try to evaluate the infinite list immediately. Okay, enough of this. Let's just do, first of all, will it try to print this out? It will. Alright. If I do say of, I don't know, 1, 6, there you go. And then what if I tried to sum that? Alright, not bad. I'm gonna hope that didn't overflow. If I look at the digits here, this is actually 17 billion. So this might be a big int. Let me see. I believe if I do type of m, I'm not sure if that's what I want, but anyway. Cycle. Okay, cool. Repeat 5. Infinite list. Alright, great. Cycle it. Replicate 3, 10. Okay, please. I don't like this because, like, no need to make a function for something which you can pretty much already do. Alright. Anyway, with that knowledge, I can probably just do this. Uh, so cycle list. And then take the just length. Okay. Oops. Okay. Hopefully this should work then. Repeat list 1, 2, 3, 3 times. And there you have it. It's not too bad. I'm sure that's not really the proper way to do it, because, maybe it's not. But either way, a lot of fun. Not bad. And that's nice. Set comprehensions. The first 10 even natural numbers means 2 times x, where x is from natural numbers, and x is less than or equal to 10. That's a predicate. In a scale, if we could do something like take 10 of those, but if we didn't want doubles, we wanted some more complex function, we could use a list comprehension for that. List comprehensions are very similar to set comprehensions. We'll stick to getting the first 10 even numbers for now. We could use x times 2, where x is from 1 through 10. I see. X times 2, where x is from 1 through 10. Very nice, very nice. As you can see, we get the desired results. Now let's add a condition. Okay, so let's say where x is not equal to 5. There you go. So now it skips 10, and it gives you 2, 4, 6, 8, 12, 14, 16, 18, and 20. But there should still, no, there should be 9 of these. Maybe, what if I did this? There we go. That's something that you absolutely could do. It's their map function. Okay. Can I also map 1 through and then, ooh. X. Begging? No, that is not it. Map has 1 value argument, but its type has none. Oh, you give this the... Wait. Okay. Take 10 from that. Hey, that's nice, that's nice, that's nice. Can I also do this? That is very nice. Carrying my beloved brow. That's great. That is very, very cool. So it says take 10 of what the list you get from mapping +1 onto 1 through etc. Right? So what did I could do with that? It's smart enough to figure that out for me. Well, x is drawn from 1 through 10, and for every element of 1 through 10, we get that element only doubled. As you can see, we get the desired results. Now let's add some precondition. Note that weeding out lists by predicates is also called filtering. We took a list of numbers and we filtered them by the predicate. Takes a list, replaces each odd number greater than 10 with bang, each odd number less than 10 with boom. So like this. Very cool. The last part of the comprehension is the predicate. A function odd returns true on an odd number, false on an even one. Easy enough, easy enough. We can include several predicates. If we wanted all numbers from 1 to 10 that are not 13, 15, or 19, we'll do attached. Is there now any way, I wonder, to no. Maybe this is what I want. There's actually a not function for booleans. Alright, that's just past currently where I am. So let me just rewrite this though as x from where there you go, same result. Easy enough. And this includes 20. So can I do this? No, I cannot. Not only because we have multiple predicates, we can also draw from several lists. Alright, now this is very nice. All possible products that are more than 50. So here's the thing about this. I don't know whether it's calculating this twice. That's the thing about Haskell. You don't really know whether it's doing that twice. So I feel like you could still optimize it to but that doesn't do it, does it? So greater than 50 then. Now I wonder, this might be a bit better. Personally, I like it a bit more than that. Oh, okay, sure enough. Let's write our own version of length. We'll call it. Ooh. Oh, that's very nice. It says take one from everything in excess. Let's that's pretty cool, honestly. 3. Alright. Because strings are lists, we can use list comprehensions to process and produce strings. Here's a function that takes a string and removes everything except uppercase letters from it. All good. Nested comprehensions are also possible. You're operating on lists that contain lists. Okay. Some ways tuples are like lists. Alright, I know what a tuple is. Should be easy. Come on. There are a few fundamental differences. A list of numbers is a list of numbers. That's its type, and it doesn't matter if it only has one number in it or an infinite amount of numbers. Okay. Tuples, however, are used when you know exactly. Right. This I know. You know exactly how much is in there. We use parentheses. Right. This again, I know this. Should be good. This, I don't think I really have to read all this. FST takes a pair. Okay. Not my favorite. names for stuff, but FSTSND, whatever. Cool function that produces a list of pairs is zip. Yes, it is. Takes two lists, zips them together into one list. And then it returns tuples. Very brilliant. Very nice. Pairs up the element, produces a new list. First element goes with the list, the first, second with the second, etc. So basically, quick drawing here. You have your list of a okay, I guess I'm not doing that. Let me use color paint. I have a list of A, B, C, D, E, F, and this is the list, right? And it keeps going on. Then we have a list of, say, 1, 2, 3, 4, 5, 6, etc. So what it will do is it will give you this, comma, this, comma, this, comma, this. So a list of all these red circles, right? And you can deal with them. It's very useful. I use it all the time in Rust and also from other languages, so like Kotlin and stuff. Definitely a very useful one. Yeah, so these are triangles. So then allow me to print the triangles. Here they are. Now, if you evaluate that by typing out triangles, you'll get a list of all possible triangles with sides under or equal to 10. Let's add a condition that they all have to be right triangles. Also modify this function by taking into consideration that side B isn't larger than the hypotenuse and that side A isn't larger than side B. Okay. Oh, so power of not bitwise or. So if I do this, how do I do or then? Bitwise or Haskell. Okay, so this defines bitwise operations. You have or, XOR, complement. We're just drawing from 3 lists and they're combining into a triple. So let me do this. Okay, hold on. Let triangles equals this. Let right triangles equals triangles filter A, B, C into You would need pattern matching. You know what? Let's write this out. Let's put this right here in my thing, right? Triangles equals this. So these are my triangles. Now, with that said, these is triangle good T equals a squared plus b squared equals c squared. But hey, I think that's right. Now, good triangles equals filter is triangle good? Triangles. Yeah, that's very nice. That is very cool. Really brilliant mathematical stuff. This is definitely something I could have a lot of fun with. Can I dark mode this? I guess not. Okay. We want ones where the perimeter is 24. Okay. And a plus b plus c equals 24. And now, if I do good triangles, again, I should just get 6, 8, 10. Yes, right. So you don't want duplicates. So let's make C here, B here. Now we should not get any duplicates. And there you go. Let's say we want to remove this. And say we want, I don't know, 80. Why not? Here you are. There's are your triangles. That's with the biggest side being 80. So it's very elegant. It is definitely very elegant. You look at it and it's like, wow, that is nice. That is really nice. I didn't even have to write type definitions. I mean, it could just basically figure it out. I could even like take it to the limits here and just say 200, right? Why not? It'll just take a second to generate. But here they are. But I mean, here's the thing. In Rust, that would be basically instant, right? So allow me to hit this in Rust now. The uh, oops. If a dot a squared plus b squared equals c squared, triangles dot push ABC, and now debug the triangles. Like this would be basically instant. All right, so clearly something up here with that. Okay, first of all, we should start these at 1, right? Excuse me? That shouldn't really be happening. Obviously, debugging it takes a while, but a squared plus b squared equals c squared. Oh, right. I have these in the wrong order. I'll make this c. I'll make this c. Make this. Okay, now it should work. And you can see it is basically instant, which is why it's like it's a lot faster than what I had to do here. Like this took a while. And this, like, if I wanted to time it, it would be basically instant. So there's a big speed difference. But you know what? Why not? Just some Haskell and Obviously here it's cached now, but it's fair enough. With that said, I think I'm done for today. I think I have had enough Haskell. We have gotten here. We finished that chapter. Next, we have the next chapter. And all that. So, thank you guys for watching. The 0 viewers. I appreciate it. And next week, I will keep, well, not next week, maybe tomorrow, maybe even later today, I'll keep learning my Haskell. Thank you guys.